project. Project Gemini was the first ever collaboration between astronautics truck and robotics truck from mechanical engineering, and our project manager, Catherine Ayotte, is going to start it up.
Before I begin, has every panelist received a binder with our slides? I just want to be sure that everyone got one. Thank you. All right. Well, good morning, everyone. Thank you so much for attending our system validation review today. As Dr. Benavides said, my name is Catherine Ayotte, and I will be introducing Coeus Promethia Genna to go over our side of Project Gemini. An overview of what we'll be discussing today, I'll be introducing our full design team, followed by our mission overview, concept of operations, system of systems definition, followed by each of our performance metrics for the chase vehicle, target vehicle, and visual tracking systems, followed by the entire Gemini system of systems mission. This will be followed by some of our configuration management, as well as our conclusions and programmatics. At this time, I'd like to introduce Nina Rogerson, our assistant project manager, Raul Gonzalez, our chase vehicle team lead, Yashika Khatri, chase vehicle team, Matthew Klockner, chase vehicle team, Tripti Mahendrikar, chase vehicle team, Patrick Bright, our target vehicle lead, Lee Morris, visual tracking lead, Seven Reinhardt, integration, Rachel Pope, integration, and Noor Rashid, integration. So Project Gemini is an emulated planar environment for satellite refueling mission, which is a simulation of an in-orbit satellite rendezvous maneuver similar to NASA's Restore L project. In order to achieve this on our side of the mission, our team created 3 different systems: a chase vehicle system, Castor, a target vehicle system, Pollux, and not pictured, an overhead visual tracking system to watch the vehicles during their demonstration. We also interfaced with Sparta Robotics, who we just got to see present on their system, for the robotic manipulator capture system between those 2 vehicles. In our presentation, we focused more heavily on the objectives that our systems were able to complete, as well as a brief overview of what the robotic manipulator was capable of during this mission. Our concept of operations begins with the startup phase, where the chase vehicle system is positioned on the demonstration platform and is hovering using air bearings at this time. It also has the robotic manipulator mounted on board and is communicating electronically at this time. The target vehicle system is positioned on the other end of the demonstration platform, and the visual tracking system overhead observes the entire demonstration platform with a camera to determine position and orientation of the vehicles. During the approach mission phase, the chase vehicle system translates using a compressed air propulsion system to the target vehicle system, at which point it completes station keeping within a range of the target vehicle system. During the docking, the robotic manipulator reaches out and grabs onto the target vehicle and pulls the 2 vehicles together, at which time they electromagnetically dock with each other. Then, the robotic manipulator completes a refueling maneuver in which it uses its camera vision to locate the refueling receptacle on the target vehicle and inserts a barrel plug into a capacitive circuit, which constitutes the refueling of the target vehicle. During the undocking and return, the robotic manipulator repositions itself on top of the vehicle. The chase vehicle translates back to its initial starting position using coordinates from the overhead tracking system, and once it reaches that position, performs station keeping, constituting the completion of the mission. At this time, I'd like to hand it over to Nina Rogerson to go over our system of systems.
Thank you, Catherine. Hello, everyone. I am Nina Rogerson, and I'll be going over the system of systems. The system of systems objectives are that the system of systems should consist of a chase vehicle system, a target vehicle system, a visual tracking system, and a robotic manipulator system. It should have a startup, an approach, a docking, a refueling, an undocking, and a return mission phase. It should complete a rendezvous maneuver between the chase vehicle system and the target vehicle system during the docking mission phase. And it should deploy the robotic manipulator from the chase vehicle system during the docking mission phase. And it should complete a rendezvous maneuver, or refueling maneuver, between the 2 vehicles during the refueling mission phase. It should also use the visual tracking system to determine the position and orientation of both the vehicles throughout the mission. First, we have our full systems. Here we have Castor, the chase vehicle system with the robotic manipulator on board. We have the target vehicle system and the visual tracking system above. First off, with the chase vehicle system. The chase vehicle system is designed to hover and translate across the demonstration platform towards the target vehicle system and support the robotic manipulator. It does this by having its compressed air supply at the back, and it has 2 visual tracking nodes for the visual tracking system to see where it is at all times. It also has the docking interface to support the docking with the target vehicle, and the air rings and nozzles on the sides to support the translation and hovering mechanism. Next, we have the robotic manipulator added on top. It is securely mounted using its manipulator mount here. It has this end effector here, which will be what grabs onto the target vehicle system and pulls us in for the docking phase. And then it has this charging port in the center of the end effector, which is what will actually perform the refueling mechanism. Next, we have the target vehicle system. The target vehicle is to remain stationary throughout the mission and support the refueling electronics. It does this by having the refueling receptacle in the center for the charging port on the end effector to connect directly into. It also has visual tracking nodes for the visual tracking system to see where it is at all times. It has a docking interface here for it to support the docking with the chase vehicle system, and it has a capture point here to support the capturing from the end effector. Last but not least, we have the visual tracking system. The visual tracking system is to watch both vehicles throughout the mission. It does this by having a mounting frame so that it's positioned directly over the center of the demonstration platform. It has a camera centered here so that it can see everything as it goes along. And it has a computer, Arduino, Omega, and Bluetooth so that it can do its communications. Next, I would like to introduce Raul Gonzalez to talk about the chase vehicle system.
Thank you, Nina. Good morning. I am Raul Gonzalez, Chase Vehicle System Team Lead. The system key objectives for the Chase Vehicle System were drafted in order to simulate rendezvous, docking, and refueling maneuver. These objectives state that the vehicle shall hover over a demonstration platform, translate in a two-dimensional plane, and rotate about its z-axis. Finally, the vehicle should interface with a robotic manipulator, should be autonomous, and should dock with the target vehicle system. In order to meet these objectives, the following requirements were drafted. The electrical key requirements state that the battery component shall have a voltage greater than or equal to 14 volts, shall have a capacity greater than or equal to 3.8 ampere hours, and shall have a maximum current discharge greater than or equal to 5.7 amps. Similarly, the voltage regulator shall step down the voltage to a range of 10.8 and 12 volts, and shall have a maximum discharge current of 5.7 amps. Moving on to the docking interface key requirements, these requirements state that the component shall magnetically attract to the target vehicle system at a distance no greater than 2 millimeters and send a signal to the robotic manipulator upon docking at a distance no greater than 0 millimeters. In this render, the two electromagnets used are shown in black. The propulsion key requirements state that the translation mechanism shall allow the vehicle to have a velocity no greater than 0.2 meters per second while operating in an ISO standard 85731, quality class 7 or greater, while the chase vehicle system shall be able to rotate 360 degrees about its yaw-axis. Moving on to the microcontroller key requirements, these requirements state that the microcontroller shall be able to send and receive data to and from the robotic manipulator at a baud rate of 115,200 bits per second, shall compute the desired position and orientation, as well as the required reaction to maintain set position and orientation in a frequency loop of 20 Hz, and shall operate the solenoids to maintain set position and orientation at a frequency of 10 Hz. With the microcontroller key requirements, the solenoid driver component has two requirements stating that the driver component shall have a current rating greater than or equal to 2 amps and shall have a voltage rating greater than or equal to 12 volts. The solenoid driver component is what allows our microcontroller to control the solenoids. And now I would like to pass it off to Matthew Klockner to talk about the electrical validation of the chase vehicle system.
Thank you, Raul. My name is Matthew Klockner. I'll begin by going over the electrical validation. Please note, for each electrical validation test, we performed a general procedure where we constructed the shown circuit and measured the associated test metric. Beginning with the battery component, our first test metric was measuring the voltage output of our battery. To do this, we measured the voltage as our battery discharged from a fully charged state of around 14.8 volts until it reached under 12 volts, where we considered it fully discharged. Here's some of our data that we took during our test. From this data, we were able to find an average to calculate our nominal voltage for the battery to meet our requirement. This value is calculated to be 13.41 volts for our battery, which was within our test range, satisfying our requirement and passing the test. We would recommend, however, that during this test, our resistor became very hot as it was dissipating over 70 watts worth of power. So we'd recommend, for the safety of the test personnel, to have a heat sink or other way of dissipating this heat. The next metric was the current for the battery. Following our general procedure, we were able to measure this current. This measured current had a maximum current of 7.08 amperes, which satisfied our requirement and passed the test. We have no recommendations. Our final test metric for the battery component was the capacity of our battery. In similar fashion to the voltage test, we measured the voltage of the battery as it discharged from a fully charged state to under 12 volts, taking samples at set time intervals. From this data, we were able to calculate our total battery capacity to be 5.59 ampere hours, which surpassed the required 3.85 ampere hours, passing the test and validating our requirements. We also recommend the same safety precautions for the resistor. Next, I'll be going over our voltage regulator component. The first test metric for our voltage regulator component was the output voltage. Following our general test procedure, we were able to measure a total output voltage of 11.99 volts, validating our requirement and passing the test. We would recommend using a constant voltage supply, as that will decrease the fluctuations in voltage throughout the test. Our next test metric was the current of the voltage regulator component. Following our general test procedure, we were able to measure this current value. This measured value was 5.7 amperes, validating our requirement and passing the test. We would recommend actually combining the current test and voltage test for the voltage regulator into one test, as they use the same circuit and are very easy to go between measuring the voltage and the current. Next, I'll be going over our docking validation. The first test metric for our docking validation was the electromagnetic attraction. In order to test this, we positioned the target vehicle system and the chase vehicle system's docking interface components 2 millimeters apart. We uploaded a Arduino test program to turn on the electromagnets to attract the two ports together, and then we verified that these two ports were actually in contact with each other. The result of this test is successfully completed docking, where the two interfaces were in contact with each other after the program was uploaded. However, we did notice that while the electromagnets were able to attract the two interfaces together, that the force that they held each other was not sufficient to hold the two systems together while the robotic manipulator was moving and applying torques to the system. To fix this problem, our solution was to actually move the electromagnets to the plane of the two docking interfaces so that there was a stronger magnetic field there. This actually was able to withstand the torques that we experienced during this test. The next test metric was the docking circuit connection. Similarly, we positioned the two vehicles within the 2 millimeters, uploaded the Arduino test program, and then monitored the input pin on the Arduino associated with the electrical circuit completed by the two electrical strips on our docking interface. For our first test, we actually did not pass this test, as misalignment in the docking interfaces, as well as differences in the tolerancing of the strips and the flatnesses of the the docking interface components, made it so that there's actually a misalignment between the top electrical strip and the bottom electrical strip, meaning that when we were in contact and docked, the two electrical strips were not in contact with the target vehicle system's docking interface, meaning that that electrical circuit was not able to be completed. To fix this, our solution was to cut the top strip, electrical strip, into two, effectively doing the same thing as the two strips on top and bottom. However, since they're both on the same plane, they were both able to make that connection when we were docked. When we ran this test, we were able to successfully complete the circuit, resulting in a 0 reading from our input pin, and verifying that our docking distance was 0 millimeters. We'd recommend, to avoid this problem, to create a tighter tolerancing of our electrical strips, the docking interfaces, so that this problem doesn't come up in future testing. Next, I'd like to hand it off to Tripti Mahanagar to go over our propulsion validation.
Thank you, Matt. Hello all, I'm Tripti Mahanagar, and I'll be talking about the validation tests that were conducted for the propulsion system. First, I would like to talk about the test that was conducted for the solenoid operation. Our requirement was that the solenoid should operate at a pressure greater than or equal to 13 kilopascals and under ISO standards 8573.1 for quality class 7. The test process that we used to conduct this test was we wrote a code to actuate either the X or the Y thrusters, and then we placed the chase vehicle system on the demonstration platform, and we observed the motion of the vehicle. When we first conducted the test, we did not have nozzles. We had a 4mm wide opening of the tubing itself. So we made some design changes. We included converging nozzles because initially we were not able to generate enough thrust to set our vehicle into motion. So using compressible flow equation, we were able to design these nozzles which were capable of setting the chase vehicle system in motion. The solenoids were operated at 75 psig, which is way greater than 13 kilopascals, which converts into 1.89 psig, and it was operated under ISO standards 8573.1 quality class 7. So we validated our test and we passed the test. One of the recommendations that we have for this test is to include a requirement that talks about specific thrust generation. This would have reduced any complications or all the complications that we came across during the validation test phase. The next test metrics that was validated was the velocity. Our requirement was the chase vehicle should translate under 0.2 meters per second. The test process that we used to conduct this test was we placed the chase vehicle system at one of the extreme ends of the demonstration platform. We turned on the VTS and recorded the position of the chase vehicle system. We wrote a test code to once again actuate either X or the Y thruster, and we allowed the chase vehicle to translate to the opposite extreme end of the demonstration platform. We ran 4 tests for accuracy. This is the first test that was analyzed. The red line here represents the 0.2 meters per second requirement that comes from our OCR. And the transparent line in blue is the velocity that is directly calculated from the VTS data or the visual tracking data that was recorded. And the transparent line in green is the velocity in the Y direction that was recorded by the visual tracking data. So as you can see, there are a lot of oscillations, and this was because at that time, VTS had errors of 0. Or actually around 100 millimeters or so. So when we differentiated the position with respect to time, it amplified the error. So we had to take moving average over the velocity, and the line that is etched in dark blue is the moving average of Y velocity, and the line that's etched in green is the moving average of the X velocity. So as you can see, we did not meet the requirement. We crossed the 0.2 meters per second requirement while translating in the Y direction, that is the Y velocity line. Moving on to test 2, you can see the same exact results. Once again, we crossed the 0.2 meters per second requirement in the Y direction velocity. And in test 3, we exceeded the 0.2 meters per second in the x direction, and this was because the chase vehicle was translating in x rather than in y this time. And in test 4, it exceeded in the y direction because we changed the orientation again. So the maximum recorded velocity, the absolute value, which is also the speed, is 0.5 meters per second. So this value exceeds our requirement, and thus we failed the test. But the reason we failed the test was because when we did our preliminary calculation, we did not account for any torques or disturbances that were acting on the chase vehicle system due to the feed lines that were going to the solenoids and the air bearings. And also, we did not have a controller when we ran this test. And in the real mission, when the chase vehicle translates on the demonstration platform, it uses a controller. So the speed is always controlled. And also, we should have specified speed instead of velocity in our requirement, as speed is what determines the motion of the vehicle during the test. The next test that was validated was the rotation test. Our requirement was the chase vehicle should be able to turn 360 degrees about its yaw axis. So to conduct this test, we positioned the chase vehicle system on the demonstration platform with its air bearings and solenoids functioning. We wrote the test code to actuate either the counterclockwise or the clockwise rotating solenoids. And as you can see, the chase vehicle is capable of rotating about its yaw axis. And we validated our test. We do not have any recommendations for this test. Now, I would like to invite Yashika Khatri to talk about the controller validation.
Thank you, Trupti. Hello everyone, I'm Yashika and I'll be going over the controller validation, starting with the solenoid driver. As Raul said, the solenoid drivers actuate our solenoids to be able to activate thrusters for translation and rotation. Our first requirement that we validated was for the current of the solenoid driver to be rated for greater than or equal to 2 amperes. To satisfy this requirement, we had a test process where we sent power to the solenoid driver at 12 volts and 2 amperes and recorded the output. As you can see, all of the channels output a current of greater than 2 amperes, thus meeting our requirements. For our recommendations, the first issue we faced was that more than two solenoids weren't actuated by the solenoid driver because of a limit of power draw from the Arduino and not sufficient grounding. Because of this, we created an opto-isolated system using 3 AA batteries, which helped us actuate multiple solenoids at the same time. Along with that, another issue we had was, as Raul mentioned, the actuation requirement for us was at 10 Hz, but the solenoid driver could only operate at 5 Hz. The next test validated was for the voltage of the solenoid driver component, which was for 12 volts. Similar to the last test, we sent power to the solenoid driver at 12 volts and 2 amperes and exceeded the 12 volt output in each of the channels, thus meeting our requirements. Our recommendations are same as the last one. The next test validated was for the microcontroller component and for it to communicate with the robotic manipulator system at 115,200 bits per second baud rate. The test process was we connected the Jetson and the Arduino Mega physically, and we sent a code to establish serial communication. We were successfully able to establish the serial communication at the rate specified. We have no recommendations for this test. The next requirement was for the control loop to operate at 20 Hz. For this, we had a test code, we received BTS data, and actuated our control loop and recorded the frequency output, which was 20 Hz, thus satisfying our requirement. A recommendation for this would be using our actual control code rather than using a test code so we can verify that our actual control code works at the same frequency. Our next requirement validated was for the actuation frequency of 10 Hz for the solenoid drivers. We sent this message to the solenoid drivers to be able to actuate at this frequency and printed out the results of the frequency from the actuation loop, which we received 10 Hz, thus verifying our requirements. A recommendation for this would be not to cut the control loop frequency in half because there's no reason to go down and dumb down our system more. Instead, we could have used 20 Hz of the control loop frequency as the actuation frequency as well. Some of the disadvantages we faced having requirements for the microcontroller component were that we didn't take into account the mission objectives, the mission phases, or the software part of the microcontroller. We only focused on the hardware parts, which was a very big issue. Here you can see the chase vehicle system station key. Something we would change in the future and some requirements we would add would help us establish the software as well. Something we would add for that is the type of control logic we use. Currently we are using a deadline controller. We would also add a requirement to hold the position in X, Y, and theta directions to be able to station keep within certain limits. We would also have a requirement to be able to stabilize in a specific amount of time, because we don't want to be sitting there forever waiting for it to stabilize. Another requirement we would have is for the BTS data coming in so that it's more accurate and usable for us. We had to add a smoothing factor to make that happen. Another requirement we would have is for the navigation path generation. No matter where chase vehicle system and target vehicle system are, we should have a navigation path optimized that can take us there in least amount of time and most optimization. I'll now be passing it over to Patrick Wright to go over the target vehicle system validation.
Thank you, Yashika. As she said, my name is Patrick Wright, and I'll be going over the validation of our target vehicle system. The objective of the target vehicle system is for it to remain stationary on a demonstration platform for the duration of the mission. It is also required to accommodate an electrical refueling maneuver, receive electrical current from the robotic manipulator system, store the electrical charge transferred from the robotic manipulator system, and use the electrical charge stored to provide a visual confirmation of a successful refueling. To achieve these objectives, two main requirements were derived. The first was related to stability, stating that the geometric center of the target vehicle system shall remain within a 5 centimeter radius of its initial position for the duration of the mission. The second was related to compatibility, stating that the refueling receptacle subsystem shall accommodate a 3.7 volt electrical input from the robotic manipulator. On the next slide, there is an animation of what we did to validate the first test. To validate the first requirement, we placed an outline of the 5 centimeter boundary on the demonstration platform and proceeded to center the target vehicle system within said boundary. We then attached the end effector of the robotic manipulator system to the grab ring of the target vehicle system and proceeded to pull with the robotic manipulator, as shown in the animation. During this test, we observed that only the chase vehicle system moved. Based on this observation, it was considered that our requirement was validated. It is important to note that during this test, not all servos in the robotic manipulator system were active. One recommendation to improve the quality of the test would be to have all servos active. This was not possible at the time due to production setbacks with the robotic manipulator system. To validate the second requirement, we set the output of an external power unit to the required 3.7 volts and attached the leads to a barrel plug on board the target vehicle system. During this test, we observed that the LED was lit, suggesting that the circuit was operating as designed, thus validating our requirement. One recommendation to improve this test would be to actually have the fully assembled robotic manipulator provide the electrical charge instead of a power unit, but that was not possible at the time of this test because of the difference in timeline, production timeline between Sparta Robotics and our team. Now I'll hand it over to Lee Morris, who will discuss our validation of the visual tracking system.
Thank you, Patrick. As you said, my name is Lee Morris, and I'll be discussing the validation of our visual tracking system. The objectives that we determined for the visual tracking system were that it should be able to view the entirety of the demonstration platform within its field of view. It should be able to determine the absolute position and orientation of the chase and target vehicle systems, and it should transmit that position and orientation data to the chase vehicle system. Based on these objectives, we determined the requirements for the visual tracking system to be that it should view the demonstration platform with a resolution of 0.5 centimeter per pixel or greater. It should capture images at a frame rate of 20 frames per second or greater. It should transmit data to the chase vehicle system at 9,600 bits per second or greater and at a range of 4 meters or greater. And it should determine the absolute position and orientation of the chase and target vehicle systems to an accuracy of plus or minus 1 centimeter and plus or minus 5 degrees. In validating these requirements, the first test that we performed was to test the view resolution of the demonstration platform. This involved a program that analyzed images taken from the camera subsystem. In the program, the user pinpointed the location of the boundaries of the demonstration platform, and the program output the resulting view resolution. This program, as well as all the other programs I'll be discussing in this section, was written in Python and primarily used the OpenCV computer vision library. The results from this program showed a result of 0.446 centimeter per pixel in the horizontal direction, 0.452 centimeter per pixel in the vertical direction. Numerical analysis based on measurements of the system as well as specifications of the camera predicted a value of 0.445 centimeter per pixel. This requirement was satisfied because resolution increases as this value decreases. A recommendation that we have for this test is to adjust our requirement due to the fact that the visual tracking nodes will be elevated above the demonstration platform, and therefore the view resolution within that plane will be lowered. The next test that we performed was to test the output of the camera with the frame rate. This is a very simple process in which the controller component communicated with the camera subsystem to set the frame rate and then display the resulting output. The result of this test was that the camera successfully output the required 20 frames per second, thereby passing the test. The motivation behind writing this requirement, however, was that the visual tracking system as a whole should perform all operations at 20 Hz. And while camera frame rate is a critical part of this process, it is not the sole determining factor. So another test should be written to validate this requirement and to write the new requirement for that. However, in informal testing of our system, we did find that the visual tracking system was capable of performing all operations at 20 Hz. The next test that we performed was to test the communication capabilities. A program was written for the visual tracking system to transmit data and to establish a serial link with the chase vehicle system and to transmit data at 38,400 bits per second. The two systems were placed 6 meters apart, and data being received by the chase vehicle system was monitored with the computer. The results of this test were that the systems were able to successfully transmit data within our required parameters. This satisfied both the requirements of the chase vehicle system and the visual tracking system, which included the same communications hardware. The last test that we performed was to test the position and orientation determination accuracy of the visual tracking system. This process involved writing a program, again in Python using OpenCV, to determine the position and orientation based on the viewed location of the visual tracking nodes. The mock visual tracking nodes were printed to the exact specifications of those on board the chase and target vehicle systems and were placed at various positions and orientations on the demonstration platform. The error between the output of the visual tracking system and measured values was then averaged over a period of 5 trials to validate a requirement. After 3 attempts, with improvements to software being made between each attempt to improve the position and orientation determination accuracy, the visual tracking system successfully passed all the requirements as you can see in this table. A recommendation that we have for this test is to make the test scenario identical to system operation conditions using the individual chase and target vehicle systems to give us better confirmation of our results. We also believe that the full system of systems would work fully with a lower requirement for our accuracy. Next, I'd like to hand it off to Nora to talk about the full mission test.
That chair really scares me. Thank you, Lee. My name is Nora Rashid, and I'll be talking about the Gemini Systems of Systems full mission test. The Gemini mission phases are startup, approach, docking, refueling, undocking, and return. What I'm going to be talking about is actually the full mission, but it does not include the robotic manipulator. Here we're beginning with the startup mission phase, in which the chase vehicle powers on. The chase vehicle then begins hovering. The visual tracking system also powers on, and there's a communication link that's established between the chase vehicle system and the visual tracking system. As you can also tell from the results, all of the checklist items pass the tests. Here we have the chase vehicle system being powered on, which means the battery is plugged in and also the code is put onto the chase vehicle system. And here we have the chase vehicle system and the visual tracking system, and the communication link is established between both. As for the approach mission phase, we have the chase vehicle system translating to the target vehicle system, as well as station keeping being performed. For the results, the station keeping routine actually exceeded our expectations, as the chase vehicle system ended up docking with the target vehicle system. And here we can see the chase vehicle system approaching the target vehicle system, and as you can see, it also oscillates back and forth. This is due to the deadband controller, as it determines the relative position as it goes. And here we have the chase vehicle system going closer to the target vehicle system, and the station keeping routine happens. As for the docking mission phase, in an ideal situation, as our mission is described, we have that the chase vehicle system sends a signal to activate the robotic manipulator system. Then the robotic manipulator grabs onto the capture point on the target vehicle system. The robotic manipulator then pulls onto the chase to the docking range, and a signal is sent from the robotic manipulator to the chase vehicle to dock. This is when the electromagnets are then activated. The results for the first checklist item is actually we did not pass the test, as that didn't occur because we did not have the robotic manipulator at the time. The next 3 checklist items also did not occur for the same reason. The electromagnet activation did pass the test, as it had allowed the chase vehicle to dock with the target vehicle system. And here we have the docking phase, where we have the chase vehicle system calibrating itself back and forth when it reaches the target vehicle system. And as you can see, this takes quite a long time. It was longer than we had expected. But if we had the robotic manipulator on board, then we would have that speed up the process. We were able to achieve docking due to the high accuracy of the visual tracking system, and because we had a code for the chase vehicle system and the target vehicle system without the robotic manipulator signal. This is because the electrical strips on the chase vehicle system were able to complete a circuit, and this circuit was also used, the same implementation was used for the electromagnets. So we were able to dock with both vehicles without the robotic manipulator on board. Now I'd like to ask Rachel Polk to come up here to talk about the full mission.
Thank you, Nor. Hello everyone, my name is Rachel Pope and I'll be continuing the full mission. Continuing on with our mission phases, next we have the refueling mission phase. This consists of, ideally this would consist of the robotic manipulator releasing the grab ring and moving towards the guidance cone, as you can see in this picture. Next it will insert itself into the refueling receptacle and begin refueling. Once it has refueled, you can see that the LED will light up. This phase was incomplete due to the fact that we did not have the robotic manipulator on board the chase vehicle system. Next we have our undocking mission phase. Again, ideally we will have the robotic manipulator released from the refueling receptacle and reorient itself on top of the chase vehicle. It will then send a signal to the chase vehicle saying that we can deactivate our electromagnets. The first 3 items in this table were incomplete since we did not have the robotic manipulator. However, we were able to deactivate the electromagnets. We edited our code and were able to add a timer. Once that timer ran out, we were able to turn off the electromagnets and undock. And lastly, we have our return mission phase. This consisted of the chase vehicle translating back to the starting position and perform station keeping. And as you can see in the video, this is at the end of the undocking phase. And right now it is recalibrating and finding the starting position. It will then move back to the starting position and then perform station keeping. As you can see, we have passed this phase. Now I'd like to introduce Devin Reinhardt, who will go over our configuration management.
Thank you, Rachel. I'm Devin Reinhardt. I'll be talking about our configuration management. So our configuration management consists of a product structure tree, bill of materials, assembly drawings, part drawings, and it also includes all of our past presentations, validation tests, and reports, our design document, our design tree, and all objectives, constraints, and requirements. Everything is linked in our configuration management. So the tree on the right shows that you can go, if you start out at the product structure tree, you can get to the assembly drawing, and you can also get to the bill of materials, and from the bill of materials, you can get to all the part drawings. So I'm going to show an example of our product structure tree. At the top you have Gemini, which is our assembly, and then you have the 3 chase vehicle systems below it, or the 3 vehicles below it, the chase vehicle, the target, and the visual tracking system sub-assemblies, and below that you have all of their respective sub-assemblies. Below you see the hyperlink colored lines. You have the designation 1010, which goes to our 1005, which goes to all of our assembly drawings, and the other one goes to our bill of materials. If we were to click onto it, this would be the link to our assembly drawing example, and this is the robotic manipulator being added to our chase vehicle system. This is an example of our bill of materials. So here we have all of our part names and then all associated part numbers onto it. If you were to click on the hyperlink part number, it would take you to a part drawing example. So this is the guidance cone and grab ring with all of its dimensions with tolerancing available from the initial tree. As far as configuration management, our release status, we went ahead and uploaded all of our documents to the Embry-Riddle Aeronautical University AstroTrack database. And now I'll be passing it to Nina Rogerson, who will talk about systems validation.
Thank you, Seven. I will now be talking about the system validation. First, for our first objectives, we should have a chase vehicle system, a target vehicle system, a visual tracking system, and a robotic manipulator system. By having one of each of these systems, we therefore satisfy these requirements. For objective 2, for our startup mission phase, the driving requirements for this were the chase vehicle's battery component and the chase vehicle's and visual tracking system's communications components. All of these were also verified. For the approach mission phase, the driving requirements were the chase vehicle's microcontroller component, the chase vehicle's solenoid driver component, and the chase vehicle's system. All of these were passed. Next, for objective 2 and objective 3, we have the docking mission phase. The driving requirements for this were the chase vehicle's docking interface and the target vehicle system itself. All of these also passed. For objectives 2 and 4, we have the refueling mission phase. The driving requirement for this was the target vehicle's refueling receptacle subsystem. At the time of our mission test, we did not have the robotic manipulator, so this unfortunately was not passed. However, I have heard recent news that the robotic manipulator was actually able to perform the refueling receptacle, except for it was not on our chase vehicle. For objective 2, we have the return mission phase. The driving requirements for this were the chase vehicle's microcomponent, the chase vehicle's solenoid driver component, and the chase vehicle system itself. All of these were also verified. For objective 5 and 6, we have the visual tracking system to denote the position and orientation of both vehicles at all times. The driving requirement was the visual tracking system controller subsystem, and this was also passed. Therefore, for our 2 vehicles, we were able to pass all objectives and requirements. I'd now like to reintroduce Catherine Ayotte for the conclusion of programmatics.
Thank you, Nina. To start off our conclusions in programmatics, I'll be introducing the labor hours worked by the team during both prelim and detail. The team worked a total between all 11 members just short of 5,000 hours to make this project come to life, which we realize is a lot of time, but there was a lot of dedication and love put into this project by every member of this team. Our project budget was $1,600. We came in just under that budget at a total spent cost on 58 items of $1,527. We also did have 38 donated items, including the demonstration platform, which was a very expensive piece of equipment, thanks to the College of Engineering, which was all of those items an equivalent cost of $3,519. So our total mission equivalent cost was $5,046. We have learned so many lessons during this design process that it can't possibly be all included in one slide. The biggest thing that we've touched on throughout this presentation is the need to have complete requirements throughout the presentation, throughout the design process. One of the examples that I'll note here is one that Matt brought up is we had a requirement specifying how far away we needed to dock, but not how strongly we needed to hold the vehicles together when we got there. These were things that we found along the way while we completed our testing to better understand our own systems. And I think for all of our systems, by having better understood how these requirements would be used to drive our mission success, we would definitely have reevaluated many of our cases across the board to better define our system. However, we were still able to meet all of the mission objectives within our 3 systems just by working towards the metrics that we wanted, whether or not there was a requirement for them necessarily. The other thing that we really learned this semester especially was, again, communication, not only within our own team, but with Sparta Robotics. Previously, both teams were working towards preliminary design review, and we were very much on the same track in terms of what stages we went through along the way. This semester, though, we focused much more on documentation, simulation, and configuration management, whereas Sparta moved almost immediately into building and testing. And these were very different processes throughout, and that's the reason that we didn't have the manipulator for our full mission test, is simply due to differences in deadlines between our 2 programs. We're extremely happy that Sparta Robotics was able to complete those other mission objectives that we would have been able to present today, completing the full mission. But having better deadline management between our teams and communicating more about our expectations would have greatly helped us during that project. Last but not least, testing, testing, testing. Hardware never works exactly as expected. No matter how many times you read the specs, no matter how many times you compare to simulations, something will go wrong. And we definitely found that along the way at every level. Luckily, many of these things, we knew enough about our systems to say, this is what's happening, here's how we can fix that or replace this or work with it. But not leaving critical tests such as propulsion until 2 weeks before is definitely something that would have benefited the project. But we all had such a fun time being able to test this and learn from it. It's impossible to acknowledge everyone who has helped us along the way during this project, but we'd like to especially thank our professors, Dr. Julio Benavides, Sparta's professor, Dr. Jacopo Gentilini, and our communications professor, Dr. Matthew Haslam, as well as our sister team, Sparta Robotics, without whom this amazing mission could not have been possible. So at this time, I'd really like to open the floor to questions. Thank you so much.
And we have about 10 minutes for Q&A.
First of all, incredible job. You guys have really done some great work here. And so I'm going to make some comments here that are going to sound critical, but first of all, just absolutely fantastic job. What you've done here. And the thing that struck me at the end of that was the 5,000 hours. Essentially, that's 2.5 person years. So if you break it down, I did my math right here, that's essentially almost 3 months of person months per individual in your group working on this. That's an amazing amount of dedication.
I think the average was 450 per person throughout the project, somewhere in there.
So I applaud you. That is just phenomenal. And I think that the lesson we took out of that, which we paraphrase it at NASA as test early, test often. You got that? You're right on. So that was exceptional. I did have a couple of questions for you. One is that I noticed you had some very specific requirements. So my question to you is, did those requirements come from your mission, or did they come from the way you thought you were going to implement the building of the systems?
Definitely the latter, and that was definitely part of the lessons we learned is, we had these objectives and we knew what we wanted to meet, and I think in the early design phases we were so caught up in, okay, we got to have numbers to go with these requirements, how are we going to make that happen? And we focused too much on the hardware side of that, as Yashika mentioned specifically with the microcontroller. And if we could go back with the knowledge we have now, we would have really spent more time looking at the mission objectives and saying, what do we need to make that happen? It was really numbers, almost for the sake of numbers in some cases. But we tried to keep the mission objectives in mind regardless. So I think that was part of the success regardless of the requirements, luckily.
It was really good, but it did at some point look like your implementation was driving your design as opposed to the mission driving the design. So that would be my only observation, but that was good. I also noticed in you're going through you talked about the thrust computations that you did for that, and you observed that. How do you think that you might have been able to predict that early on? If you look back at it now when you were starting, it's like, well, maybe we should have seen that. What do you think might have been the key?
Tripti, would you like to?
We would have definitely thought about how the system would have translated, or like if we had any idea about the feed lines that were going into the system, we would have expected some sort of torques and external disturbances, and we would have taken that into account. But somehow we completely ignored that fact. Yeah, I mean, yes, so that's what happened. That's how we ran into problems when it came to thrust generation. Did I answer your question?
It does. And so the question that I would have as a follow-on is, did you do, or how much did you do as far as modeling simulation for that ahead of before implementation?
So I would like to pass it off to Robo.
So the simulation that we actually performed to calculate the expected thrust that we're going to generate was a MATLAB code simulation. What we did there is we applied 15, 10, and 5 factors of kinetic energy loss due to the friction from the air moving from the tube. We did take into account the tubing size, the temperature, the specific gas constant for the dry air that we're going to be using. And we applied different lengths, over 100 feet and 10 feet of distance. But that was as far as we could get, and we couldn't actually predict the actual friction losses that we were going to be getting from our tube vents and from our feed distribution systems. So what I would say, to actually perform a better simulation, we would have to do a computational fluid dynamics analysis that at the time we didn't have the time to actually perform such in-depth analysis. One of the reasons why we didn't think that was going to be a concern is because in the initial simulation from MATLAB, we were getting a thrust requirement of around 10 psi G, and our feed line in the lab has 100 psi G. So we knew that we could actually increase the pressure if needed.
So another great lesson from this, because there's another quote from George Box that says, "All models are wrong, some are useful." So, another one, there's a slide here that you had that talked about you should specify speed instead of velocity. Could you elaborate on that?
So velocity, obviously, it is both in x and y direction, and we wanted the chase vehicle system to translate in one direction, which was at that time impossible because we did not have a controller. And so what started happening was, because of the torques that was generated by the feed lines, the system started moving in x and y direction. So we could not really, but what we wanted to look at was the velocity of which it was translating. So that should have been the speed at which it was moving to go to its destination rather than the velocity at which it was moving.
Okay, so the isolation of the axes. Okay.
Yes.
I also noticed that did you have a rotation rate requirement?
So we initially did, but we had to take it off, if I'm not wrong. Or I'll let Catherine answer that.
Not that I recall. That was another thing that Yashika mentioned with the controllers, having specifications of how fast we should have gone in X, Y, and Z, as far as looking at the software side of things and how we would actually implement that controller, would have been some pieces of documentation that would have greatly benefited our design process in that regard.
And then I guess I think it's my last question here, is I noticed that your target base was fixed and not floating. And I noticed that from some of the movies that you had, that might have changed your results a little bit. How would you speculate that you might have changed some of your results? And the next question is, would you have passed all of your tests had it been a free base instead of a fixed base?
So in the initial request for proposal, there were actually 4 levels of objectives to meet, where the 4th level would have been both vehicles translating and both of them moving. At that point, we chose to only work to the 2nd level of the proposed objectives, which was a stationary vehicle, since when we evaluated the overall task we were undertaking, we didn't want to get ourselves in over our heads too early. If the target vehicle had been frictionless, we would have had a lot more to consider. Go ahead.
Right. There is a difference between stationary and fixed. Right? Stationary means that I've got 0 relative velocities with respect to some reference frame. Right? That's stationary. Fixed means I'm holding it in place, and so I'm reacting to any forces that come into it. So when you come in and you bumped it, right, you wouldn't have had a chance to go back and correct because it would have started drifting away from you, and that would have created a more complex problem.
For sure, and in the original proposal, to use the correct terminology, fixed would have been the correct term to use, as we would have wanted a fixed satellite that we would have had to correct for bouncing against it. So we would have had to have its own controller, its own propulsion, and its own reactive system on board to account for that. So at this time, we hadn't really considered how we would have implemented that. Realistically, something similar to how we did the chase vehicle system with the visual tracking and allowing it to station keep at that point definitely would have been something that we would consider. But if any of my team would like to add to that.
The way we're performing station keeping right now is with a deadband, and it actually performs really well if it's stationary at one point or fixed. So I think it would have been able to stay in place or correct for it if needed, because we're sending it to the initial position currently. So if target can hold this initial position and chase vehicle can reach the initial position, then we can satisfy our requirements. So we would have been able to, I think, optimistically thinking, we would have been able to achieve that.
Well, again, excellent job. Thank you very much. I really enjoyed it.
Thank you.
One of the things with requirements is, and we do this kind of at the end of JPL, is validation and verification, and Ola will probably correct me because I probably looked at these wrong. But one is checking off that you've checked what is written in the requirement. The second is, does it really do, was the requirement really what you wanted? So in your little video of the 360-degree turn, yes, it turned 360 degrees, but it also translated, and I don't think that's the intended operation. So just keep that in mind. I think you guys learned a ton. It's kind of obvious that you learned a lot. But that was one of the things that, yes, you checked off the requirement, but I think in actuality, yeah, it moving around was probably not what you intended. Great video though. The second one also, when you undocked, I didn't see a mass simulator for the arm. Was that something that you thought of during that test?
So for the full mission test, we were anticipating using the robotic manipulator, and that would have been part of our full mission test. Just unfortunately, due to deadlines, we ran that full mission this past Wednesday, and Sparta Robotics was still completing some of their testing at that time. So we had been anticipating using the manipulator throughout, and unfortunately, just due to time constraints, we didn't have the opportunity to use it. And that really just falls back into working with the schedules between the two teams to make sure that wouldn't happen in the future.
Was there a requirement, because I think the requirement was you have to have the manipulator arm to help you dock. That seems to be an implied one here. But not having that, how did you adjust to kind of be able to do those tests that you shot?
So with the accuracy of the visual tracking system, the chase vehicle was still being sent to the coordinates of the center of the target vehicle system, so it still reached that docking interface. What we did instead was the electrical strips are normally designed that when the arm pulls the two vehicles together, the strips are in contact between the two ports, which completes an electrical circuit. Normally, the manipulator would send us a signal saying it's time to turn the magnets on. So what we did was we improvised, and when the two vehicles bumped into each other, those strips got activated at a momentary instance. And we used that signal of that Boolean 0 being completed to send the signal instead. So that's how we still proved that we could dock at least, just to do as many of the mission phases as we could without the assistance of the manipulator. But it was difficult, and we actually cut the video frame because it took about 15 seconds of wobbling back and forth before it finally actually pulled together, which with the manipulator wouldn't have been an issue since we would have been told to how we expect it to be.
And what kind of interfaces were you planning to have between the arm? You said the arm was going to tell you. How did you discuss with the other team what those interfaces would be?
So throughout the mission, we've had a contract of sorts describing each of the mission phases. And throughout that, we established, okay, well, what's going to happen when we shift from one phase to another, for instance, docking to moving the arm, and how are we going to do that? So I'll use that as a case study, is those electrical strips generate a circuit that sends a Boolean signal. And then we have a serial connection between our Arduino and their NVIDIA Jetson. So for instance, when that circuit's completed, that sends a serial signal to the manipulator that they read as it's time to start moving. So we just had serial communication that was activated by a series of different switches or circuits being connected throughout the mission. In some cases, the manipulator's orientation on the vehicle was being used as a signal itself, saying, okay, we're back on top, we can leave now, turn off the magnets. So those had been anticipated, and we did test them outside of the mission. So we did hook up the two to test whether or not those serial communications were sent. And they were sent and received by both of our systems. We just didn't get to implement them during the full mission process. Does that answer your question?
And the overhead tracking in real life, we won't have somebody looking at us telling us what to do. In your plans for future work, what would you suggest for having these two talk to each other, get to each other without external input?
Let Lee Morris talk to that one.
So in the initial design phase, we designed the visual tracking system. We decided that we needed an absolute position and orientation determination system because the systems would be moving in a frictionless environment. If they're both sort of relative, they could slide off because you don't have an infinite demonstration platform, so that was an issue. So that's why we went with the overhead system. If that weren't a constraint of ours, then we would have a similar system on board with the camera on the chase vehicle system, looking at nodes that were on board the target vehicle system. Does that answer your question?
We have 5 minutes.
Okay, I'll try to keep these quick then, so the rest of the questions in. So my first question is looking at your translation testing data from the propulsion tests. We'll say slide 47.
47.
Yeah. So you know later on that these deviations led to the test failing. Do you know how much of this is actual data versus noise just from the sensors that you're using for the test?
So what we tried to do is very highly inaccurate. So we let the chase vehicle translate from one end of the demonstration platform to another, while we had a timer that recorded how long it would take the chase vehicle to translate. So based on that and how we actually observed the motion of the chase vehicle system, we tried to determine the velocity of which it was translating by taking the moving average. This is the maximum we could do. And if we did take if we did take another average of this data, then we wouldn't get the right results, because we could visually tell it was not right. So that is how we analyzed.
And then following up on this test,
Yes.
you noted it failed and you identified recommendations for correcting that. Was there any implementation of these recommendations for the retest?
Okay, so the translation code was actually completed 4 days before we conducted the final mission. So we could not really go back to the validation test and reconduct the translation test for the velocity test. So we did not reconduct the test, nor did we try to calculate the velocity again.
If I may ask.
Yes.
When we originally wrote many of the test plans, we were too focused on just looking at the small picture, let's meet this number. And going back, I think we should have rewritten this test plan using the controller. Because the controller, the way this test was written, it was as simple as we could to meet the number and move on, which was not the right approach to take with it. So if we could rewrite that test, it would have been to use the controller while it was moving in a mission setting to ensure that we were able to meet that requirement. Due to the way our schedule is structured, and it's something that we could have also improved, was having planned to have certain aspects of the controller done earlier so that we could do some of those propulsion tests with the correct implementations in place. So we were able to implement it in the sense that we did test how the translation worked as it worked, not meeting a specific requirement, looking at just the objectives. So does that answer your question?
It does, and many comments both made by the team as well as the panel have indicated that you've learned quite a bit in terms of design requirements, test requirements. That's a very powerful tool. As you mentioned, the purpose of a test is not to tell people what they want to do to see. It is to show the system you built actually does the job it's supposed to do. And then the last comment I'll make is one particular, just on formatting. Because it's interesting you can work in marketing at some point. You mentioned some areas of requirements were kind of hard to define because of the ambiguous nature of keep station. Well, actually, that one probably could define to within a margin of error, but activation translation software, things like that. It's good to note some quantifiable requirement, regardless of how trivial it is. And just following up on that, there were some formatting differences between how certain test data were presented in a table or just a multiple. And it's very nitpicky, but consistency is key sometimes.
And just to touch on that briefly, part of the issue was that the top level requirements were vague, as you said. And so what we looked to the full mission test was much more of a qualitative approach because we knew we were meeting certain objectives, even if the requirements weren't tying across very directly. So we went with a more qualitative approach, hence the differences, which in an ideal world we wouldn't have had to do. So that was something that we struggled with a little bit, was how to present those results. But thank you for the input, we really appreciate it.
That's all I have.
We have 1 minute.
Okay, here we go. I'll talk fast again. Again, like I mentioned, the Sparta team, you probably heard if you're in the back. I do think this is the right way to do capstones, and I hope that your pilot effort here sets a trend for the capstones going forward in the future, because this is the way things really work. Along those lines, I think it's important for you to keep integrated schedules between the teams and maybe interact more frequently. I think it was in your lessons learned, but not being able to hit key, those key milestones where you have critical dependencies and you're waiting on another subsystem, that will always break your schedules. So you've got to stick to those. And like Sarah pointed on, if you're waiting on the other subsystem and they're not ready, then do what you can with emulators or whatever can be done, or early prototyping. A simple prototype robotic system that could have just been thrown on top, just for the purposes of your testing. That's the only thing I would suggest.
Thank you.
Finally, technically, just one kind of minor little thing. Docking, misalignments, rotations are big. That's the hard part of the problem. Translation's easy. So keep that in mind. And I noticed in the video push off for the undocking, it looks like you use your cold gas thrusters to push away.
So in that, because it was not how the mission was planned to be, it was just that we turned off the magnets and it began to drift. The propulsion came back on immediately. So it didn't match how we anticipated the mission to work. Normally the manipulator would have released and we would have drifted away more nicely. It was cobbled together, essentially.
Okay. So if there wasn't a manipulator in the system, then standard undock would have some sort of pushers, right? Something to
Yes.
Yes. Very similar to what a shuttle would undock. So that's all I have. Excellent job. Lots of great lessons learned here. You guys did really a tremendous amount of work. Congratulations.
Thank you.